Let's say we have planet Earth, and off in the distance we have our wonderful moon. The mass of any object on Earth will be the same amount of mass on the moon. So if I have an object that is significantly ginormous, yet only has a mass of, say, 50 kilograms, obviously not to scale here, my friends. If I have an object with a mass of 50 kilograms, that 50 kilograms would be the same value whether that object was on Earth or on the moon. An object's weight is actually going to be different. The object's weight on the Earth will be different than the object's weight on the moon. Weight of an object is directly proportional to the gravitational pull on the object. The Earth has a larger mass than the moon, so the Earth is able to exert a larger gravitational pull on the object than if this same object were on the moon. If you were on a planet, say Jupiter is significantly larger than planet Earth, also not to scale. If we had that same 50 kilogram object on Jupiter, Jupiter has a much larger gravitational pull on the mass. So weight is directly proportional to the gravitational pull on any celestial body. Of course, in this class in physics, we tend to use Earth as our frame of reference more often than not. So anytime not stated in a problem where you are, you can always assume Earth. Now, we're not saying weight is gravity. We're saying weight is directly proportional to a planet's gravitational pull. We have to think about the object does indeed have mass, and that mass is the same no matter where you are. But because objects can indeed have different masses, you have to consider the fact that you need to think about mass with weight. So weight, we know, is not mass. Weight is a force, mass is inertia. Inertia is not a force. Inertia is the reluctance of an object to change its motion. So again, weight is directly proportional with mass. If you take and combine these two thoughts, this one and this one, we can get into establishing what weight is. Weight is an object that is being pulled to a planetary surface. You have a sensation of weight as you stand on a floor, you sit in a chair. You can feel that sensation. Weight is inertia being pulled by a planet's gravitational field. Weight is mass times gravity. Remember this very important thing here, that weight is not mass. The two are related. If something has more mass, then you're going to have a greater sensation of weight. Likewise, if you have a decrease in mass, then you'll have a decrease in weight. Which is why there's always that little quip in physics that you wouldn't join Weight Watchers if you want to lose weight. You really would want to join Mass Watchers, because decreases in mass will decrease your weight. Now, you could travel to the moon and experience a weight loss, but that's a very expensive weight loss program. Now, to make you feel more comfortable and confident in what seems like a new concept with you today, let's actually consider you've been working with this formula of weight is mass being pulled by a planet's surface. You've actually been dealing with this in your dynamics unit. Remember that weight is a force. Weight is a force. Mass, we'll keep as mass. Inertia, force directly proportional to mass times acceleration. Now in this case here, the acceleration is very specific. Acceleration due to gravity. Your formula for weight, your formula for, as I shortcut it, Newton's second law, it's one and the same. It's the exact same concept. Let's look at this again from the other way. Force, you're comfortable with, is mass times acceleration. What we're establishing with you today, force is a weight. Weight is a specific type of force. Weight is mass times acceleration, and the acceleration just happens to be due to gravity. So my hope is, because you've done a lot of practice with this calculation of force, that the calculations you're about to embark on are actually no different than what you've been doing. So as you move to working on weight calculations, you've done them before. Instead of saying a specific force, we were just talking in terms of forces in general. Let's make sure our units match to confirm these are the same concepts. Force, mass, acceleration, and weight is mass, acceleration due to gravity. The SI unit of force is going to be the Newton. Your SI unit of mass is the kilogram. The SI unit of acceleration is meter per second squared, which is why the Newton is defined as the amount of force needed to push or pull a kilogram through a distance of a meter each and every second. Weight is a force. The SI unit of force is a Newton. We have the mass, so unit of that mass is kilogram. Gravitational acceleration rate is meter per second squared, hence the definition of the Newton. Same units, because at the heart of everything, we are dealing with the same basic concept. Forces are felt because an acceleration is occurring on a mass. Let's look at a classic example of how you might work with the concept of mass and weight. So if the mass of an object on Earth is 420 kilograms, what is the object's weight on Earth, mass on the Moon, weight on the Moon? One of the universal constants is the fact that mass is the same no matter where you go. So the mass on the Earth is given as 420 kilograms, and the mass on the Moon will also be 420 kilograms. So we have the mass on Earth, we have the mass on the Moon. Now we need to figure out what the weight of this object is on Earth. Weight is found by taking the object's mass and multiplying by the acceleration of Earth's gravitational pull. This acceleration rate is, acceleration due to gravity. This acceleration rate is 9 81/100 meter per second squared. However, we're going to use the value of 10 meters per second squared because it's easier to catch if we're off in our work when we're dealing in this multiple of 10. So gravitational acceleration rate for planet Earth, we'll always use the good old 10 meters per second squared. So what we're back to doing is we're trying to find the weight of the object on the Earth. So weight is the mass, and the mass on Earth and on the Moon is 420 kilograms. And we're going to multiply by the gravitational rate of Earth, which is 10 meters per second squared. So the weight is 4,200 kilogram meter per second squared, or we know this is a Newton. So the weight of a 420 kilogram object on Earth is 4,200 newtons on the Moon. All right, and this last little space here so that we can keep this area for you to see everything at once. The last thing we need to do, because we just did this, last thing we need to do is figure out the weight on the moon. One way you could do it is to say, okay, the weight is the mass times the gravitational acceleration on the moon. The weight is 420 kilograms. We have to look up what that value is. But I don't want you ever have to look up the different values. Values will be given to you if you need to. Say maybe we have an object placed on Jupiter or Mars. But one fact we do know about the moon, mentioned earlier, is that the moon is 1/6 the gravitational overall effect compared to the Earth. So if we know that the Earth, all right, we do want to tidy this up a bit here. Let's get us a new page. So the mass on Earth is 420 kilograms. The mass on the moon is 420 kilograms. We found from the previous page that the weight on Earth, should have written this here, weight on Earth, the weight on Earth was 4,200 newtons. So the weight on Earth is 4,200 newtons. The weight on the moon is going to be 1/6 of that. So how many 6 pieces will go evenly, possibly, we hope, into 4,200? 6 into 42, not wholly into the 4, 7, that's 42. Divide, opposite here is subtract. So we end up with 700 newtons. And we can check to see if this is 1/6 of this, because 6 times the 700 does give you 4,200 newtons. And just to follow the steps of guide, make sure that these seem reasonable. We definitely have the same masses. That's true anywhere in the universe. And we want to be sure to see that the weight on Earth is greater than the weight on Moon, and 6 times greater for the weight on Earth. Let's look at another example. All right, this time we have the weight on the object of Earth is 55 newtons. You need to find the object's mass on Earth, mass on Moon, and weight on the Moon. So press pause. Try this on a piece of scratch paper. Don't unpause unless you've got work down to compare with. Are you sure you've done the work? Good. Let's check. What we know, and jot down what we know the weight, helps if we're writing with something. The weight on Earth is given of 55 newtons. The mass on the Earth is going to be the same as the mass on the Moon, but we need to figure that out. And we also need to find the weight on the Moon. All right, so we've been looking at how weight is the gravitational pull rate of acceleration on an object's mass. This time, we're needing to find the mass. So we need to rearrange this formula in terms of mass. So I want to isolate this variable. In order to do that, I need to divide both sides by gravity. That will have that divide to 1. So weight divided by gravity gives you an object's mass. So if we know the weight of the object on Earth is 55 newtons, I can put that into this to find its mass, because the other thing that I'm always knowing is that the gravitational pull on Earth, and you don't have to write the little e, is 10 meters per second squared. So let's take the weight of Earth, put this here, 55 newtons, and divide by, we know, gravitational acceleration rate of Earth's gravity of 10 meters per second squared. That's going to give us the mass on Earth because we're using the weight value on Earth and we're using the gravitational value of Earth. The 10 into the 55 gives us the 5.5. Now this is why I prefer that we use 10. It's a little bit easier to see, should I divide by the 10, multiply by 10, should my number be getting bigger or smaller? It just makes the calculations easier for us. Now the units, a Newton divided by a meter per second squared is going to leave you with that kilogram, which wonderfully is the SI unit of mass. So the mass on Earth is 5.5 kilograms. All right, so what would be the mass of this same object on the moon? Well, the mass of that object on the moon is going to be the same as the mass on Earth. So the mass is still 5.5 kilograms. What I'm left with is finding the weight of the object on the moon. Now I know the weight of the object on Earth is 55 newtons, and I know on the moon it's going to be a sixth of what that value is. So I need to break 55 into 6 pieces. 6 will go into the 55 9 times, so that's 54. Bring down that 0. Now here's my decimal. I want to be careful there. The 6 will go into there 1 time, and 6 minus, that'll give you a 40. Now I don't have any decimal places here, so I'm good with this 9 newtons. And you can always double check yourself that this value should indeed be 6 times this value, or 6 less of this. So this value times 6, 6 times 9, 54. Yep, we know we're in the ballpark.